Okay, welcome everyone. Today is kind of a big day. It's a big change in what we've been doing. And for some of you, it's a change for the more difficult, just a little bit of a warning. And that is, we have spent the last few weeks really just looking at matrices and, doing arithmetic of matrices, RREFing them, solving an equation with matrices or solving a system of equations with matrices. But that's pretty much what we've been doing. Today is a big change in what the course is, and there will be matrices, as we'll see in a bit. But today is a big theory day, theoretical day. So some people find this a little difficult because it's a lot of proofs, and it's not all about matrices anymore. It's about some of the key theoretical vocabulary that we have in this class. So today is like the big day for getting the big theory. So let me tell you how I'll start. Of course, I'll start with Q&A, which won't necessarily be theoretical at all. So I'll answer questions. And then I'm going to review something that happened, I believe it was our first day, it might have been our second day, and that is linear combinations. So I don't know if you remember, we talked about linear combinations a few weeks ago, and they're coming back in a big way today. So I'll review what the definition of a linear combination is for vectors. And then we're going to get into the two main key concepts for the entire course. And the first is span, and I'll talk about what that means. And the second is linear independence. So again, those are the biggies, is span and linear independence. So I'll define those terms. And today, and for a while actually, we're going to stick to friendly vectors that you're used to. And I will let you know, I do things slightly different than the book. And that's just my feeling about it. And I think you'll agree, maybe not, but my feeling is if you have a vector, does it really matter whether you write it horizontally or vertically? How you list your numbers?
No.
Yeah, I didn't think so. The book gets all into that, and I don't care. So they'll actually write down vector transpose to make it vertical looking. I don't really care. To me, a vector is a vector is a vector. So our vectors are going to be just the good old-fashioned vectors that you're used to seeing from vector calculus that you had last quarter. And we'll be looking to see what does it mean for to say what is a span of a collection of vectors, and what does it mean for a collection of vectors to be linearly independent. And then we'll have a big theorem about linear independence. So we'll see what that is. And then we'll talk about linear independence and combining vectors. Okay, and then we'll have a big theorem. And by the way, this is my name. It's not official, it's not even in the book, but I like to have a name for it because it'll help you remember what it is all about. And that is the too many vectors theorem. And basically what it says, if you have too many vectors, then they're not going to be linear independent. So we'll talk about what that means and do a little proof too. And then we'll talk about the unique representation of vectors from a linear combination if it's in the spanning set. And again, right now, you're not expected to know what I just said, but in the next couple hours, hour and 40 minutes or so, hopefully you will get that down. And then, as you might expect, this will never go away. TFAE. So how many items do we have on TFAE so far?
3.
3. Okay, by the end of today, we are going to have 4 more, I believe.
Wow.
So I think we're going to be at number 7. Okay, and remember that we're talking, there's dozens of them. We're only in week 3 of this class. So wait till we get to week 12 and the list goes on and on and on and on. So we're going to add more items to the TFAE theorem.
What's the most items that get added in a single day or a single lecture?
I'm not sure. It depends on my mood, because there's some details you put in and some details you don't. I had to think, should I add 2 or should I call it 4? I decided to give it the details and do 4. So I haven't. There's a lot of items though, and we'll see that. So again, TFE starts out with matrix, square matrix being invertible. And if you know it's invertible, what are the kind of things do you know? And if you know any of those other kind of things, then it also is invertible. So it goes back and forth and back and forth. So we'll have things about linear independence for matrices. So that is the plan of the day. And again, the warning today is that there's going to be a lot of proofs, a lot of theorems and theory, definitions that are really important. So don't just say, well, yeah, this is abstract, so I don't need to know it. No, you need to know linear independence and span. They're keywords for the rest of this entire course. So it's a big day. Okay, just like learning about what a matrix was a big day, and hopefully y'all agree with that. That if you don't know what a matrix is, you can't pass this class, right?
Yeah, probably not.
The same thing with linear independence and span. And the good news is we'll be reinforcing these ideas pretty much every day for the rest of this class. That's the good news, is that if you don't 100% get the idea, then by the end of the course, then you should have the idea as long as you keep working hard. And I want to let you know also is that the definition of vectors for you guys is what we're going to be using today. And that is basically a finite list of numbers. Isn't that what a vector is? 2, 7, 8, 3. That's a vector. Okay, it kind of looks like a point, except you usually put these pointy brackets in instead of little parentheses in. But it doesn't matter what symbol you use outside. It's just a list of numbers in an ordered list. And that's what we're going to be doing today. And as I mentioned, later in this course, we're going to have a more abstract definition of a vector, where you could be a vector, even though you're not a bunch of numbers. So that's just a big note. Okay, any questions about homework or anything from the course or anything going on?
Could we go over problem 14?
Okay, so let me go find it and copy and paste. That seemed to work last time, so 3.2 number 14, I believe. Just a minute. Let's scroll up a bit. I know you can't see it, but that's okay. Let me make a picture of it. Just a second. The picture thing is behind the Zoom. Just a second. Got it. That one?
Yes.
Okay. Oh, just a note, because I spent some time on it and there was a request for it, even though I said you could find it in the video also. I'm posting these lectures. So I'm posting the Word documents on Canvas. So if you go to Canvas and you go to the syllabus and you go to the calendar and the syllabus, the day-to-day stuff, you're going to see a link that says lecture. And then that will link to this Word document. Okay, so when this is done, then we'll have that linked. Obviously can't post it until the lecture's over because things like this I didn't know were going to happen before we started. So it won't get posted until, a little after. So the question is, find the inverse if it exists of this matrix. Okay, so, and we have e to the t cosine t sine t, e to the t negative sine t cosine t, e to the t negative cosine t negative sine t. Just a note, the book doesn't say this, but there's a name for this kind of matrix. Do you remember what it is? I talked about a couple days ago. Starts with a W.
Wronskian?
Yeah, the Wronskian. Notice this is a Wronskian because if you look at the first row, take its derivative, you get the second row, take its derivative, you get the third row. Do you see that?
Oh, yeah.
Okay. You're not responsible for knowing that this is the Wronskian, but you will be next quarter, so I figured I might as well mention it. All right, so we want to find the inverse if it exists. All right, so to find the inverse, what must we do? Again, there's some choices.
First, try to check the determinant to see what it is.
Yeah, first determinant. And the main reason for that is if the determinant is 0, why are we done?
Because the inverse doesn't
There
exist.
can't be an inverse.
Yeah, so that's one good thing. Finding the determinant tells you immediately, yes, I'm done, or nah, I still have more work to do. So let's find the determinant. And so to find the determinant, what can you do? Can
I
expand
used a
about,
computer.
huh?
I used a computer.
Okay, you can use a computer. Okay. And if you use a computer, what do you get? Remember, it only helps you use a
I
computer.
think it was 2e to the t. But I could be wrong. I don't have the homework in front of me.
Okay, because if we write it down wrong, then the next step is going to be wrong too, by the way. And I don't think I can do this quickly in my head. Maybe I can.
Yeah, it is 2e to the t.
Yeah, it looks right. 2e to the t sounds good. I think sine squared cosine. Let's see, sine squared cosine squared. Just 1 second. Yep, I get 2e to the t just doing it in my head. So determinant is 2. Let's do this as an equation. Too much Zoom stuff going on. So that's going to be 2e to the t. All right. And what are we looking at? What's the point of finding the determinant at the first point?
To see if there is an inverse.
Yeah, we're going to see if there is an inverse. And what are we looking for? Like what's the determination?
If there's any t value in which the
makes
determinant
it
will be
0.
0.
Right. Now, are there any t's such that 2e to the t is 0?
No.
No.
No. 2e to the t is always a positive number, never 0. So one thing is we can immediately say that the determinant is 2e to the t, and then we could say that that is not equal to 0. Good with that? Okay, and the good news is that once you found the determinant, we're part of the way there, so then we might as well use the adjoint formula. Is that clear? So let's use the adjoint formula now to find out what the inverse is of this matrix. Any questions on that idea? Okay, so what we do is, let me just go, I'll just call it A11 and do one little piece at a time. Yeah, exactly. We're going to find the cofactor matrix to find the adjoint. So I'm going to call it A11. Maybe I'll call it C11 for cofactor. Might make more sense as a letter. So C1 up sub 11. Okay, and the nice thing, I'm not sure if you could do this in your head, but if you get rid of the first row in the first column and then take a determinant, you get sine squared plus cosine squared.
1.
Exactly. Did I lose you? I just want to make sure that, again, I'm doing stuff in my head and want to make sure that you're not lost because of it. Any questions on that, why that's 1?
No.
Okay, that's C11. So I'm just going to write them out. C12. So first row, second column now. All right, so now we're going to get rid of the first row and second column. Okay, and when you do that, you get e to the t times negative sine of t minus e to the t times cosine of t. And since it's at the 1, 2, which is 1 plus 2 is odd, we multiply by negative 1. I'm going to pull out an e to the t. And I get e to the t times parentheses sine t plus cosine t. Anyone lost on that? Okay, now we do the next one. So it's going to be a bunch. So let's go on C13. So I get rid of the first row, third column. And if you get rid of the first row, third column, you get, notice it's going to be a 1 plus 3 is 4. That makes it positive. And when you have positive, that's going to be e to the t times negative cosine t minus e to the t times negative sine t. So what we get is, again, in fact, I can realize that actually one's negative, one's positive. You get sine t minus cosine t if I did everything right. Any questions on this? Okay, so now what we can say is that A inverse so A inverse is equal to 1 over the determinant, which is e to the negative t over 2. It's over 2. All right, so I'm going to have a 1 for C11. Where does the second part go? Where does e to the t times sine of t plus cosine t go?
Goes to sine t plus cosine t over 2.
No, but where in the matrix does it go?
Oh, in second column, first row.
Yeah, so notice it's the second column. No, one more guess.
It's second row, first column.
Yeah, because remember, we're taking a transpose. So instead of first row, second column, it's first column, second row, because you switch the role of row and column. So that means this guy here is going to be e to the t times sine of t plus cosine t. Okay, and where does the e to the t sine of t minus cosine t go?
Underneath that.
Yeah, that's going to be the third row, first column, because again, you switch. E to the t times sine of t minus cosine of t. Any questions on that? Now, I don't want to spend all day doing this, because we got to get to new material too. But do you get the idea?
Yeah, I caught my mistake already. It's always, every time with one of these matrix problems, it's always some small mistake I made with I'm sorry, I feel kind of stupid.
Yeah, there's a lot of mistakes made, and I make mistakes too, especially like minus sign mistakes. I'm always making those. But there's definitely mistakes. The most important thing is you understand it. So don't spend all your time trying to make it like perfect with minus signs and stuff. You should spend your time making sure you understand it. That's the most important thing. So hopefully you can see that you can get the other 6 entries. It's just busy work, but you can do it. Same idea. Any questions on that? Okay. Any other quick questions before we move on? Okay, if there's no questions, who remembers what it means to have a linear combination of vectors? That happened 2 weeks ago.
When you have multiple vectors that are connected somehow, like through a shared variable.
They're connected somehow, but how is that somehow? And that's what the word linear is, and that's the important thing. So let me remind you of the definition. Which says that suppose you have vectors, v1 through vk, then a linear combination of these vectors is a vector of the form summation I equals 0 through k. Oh, you know what? I better make that a 1. I'm so used to computer programming that I always start at 0. Summation equals from 0 to k of civi, which is the same thing, by the way, just if you like with plus signs instead, that's totally up to you. C1 V1 plus C2 V2 plus ... plus CK VK. Any questions on that? So again, this happened a while ago, 2 weeks ago, in fact, but it's a very important definition, and we're going to be using it in a big way today. Any questions on that? Okay, so for example, let's suppose that V equals, how about 2, 1, 3? And let's say W is equal to 4, 0, 1. So is 0, 1, 2 a linear combination of V and W? How do you decide? How do you figure out if it is or isn't? Any thoughts?
You try adding the vectors.
Yeah, but not just adding the vectors. You get a little more than that. Okay, you write it down in general. So you say, instead of C1 and C2, I'm going to call it A and B, just as less typing. So I'm going to say, well, the question is, can we write 0, 1, 2 in the form AV plus BW? Can that be written, I'll write equal question mark, 0, 1, 2? If the answer is yes, then it's a linear combination. If the answer is no, then it's not a linear combination. Any questions on that? And I can continue and now plug in all the numbers. So we can say that A times 213 plus B times 401 and the question is that equal to 0, 1, 2? Any questions on this idea? So does there exist an A and a B such that you get equality, or do you end up not getting an answer? Is that clear? What can I do from here?
Basically a system of equations.
Yeah, I can write this as a system, so I can look at the first component, the second component, and the third component, and those will be each different equations. So I get 2A plus 4B is equal to 0. I get A, or 1A, however you want to write it. Let me write 1A just for fun, plus 0B is equal to 1. I know it's weird to write 0B, but it's going to help us later. And then we can say 3A plus 1B is equal to 2. Any questions on that? Okay, now given that what we've been doing the last couple weeks, what can I do next? The hint is use what we've been doing the last couple weeks.
A
Matrix.
determinant.
Yeah, not a determinant, but a matrix. One step at a time. You can think about determinant, but actually determinant's not going to help. It's the matrix that we map, that we care about. So we can get the matrix out of this. And let's do that. So I'm going to insert symbol matrix. And we get 2, 4, 0. We get 1, 0, 1. And we get 3, 1, 2. So notice that we started with a question that was just about vectors. And now we have a question about a matrix. What are we looking at? What should we do next?
We can RREF.
Yeah, we can RREF. And actually, you don't even need to RREF because we don't need to know what A and B are. We just want to know, is there an A and a B? Does that make sense? So REF is good enough. Is that clear? So what I can do is REF. I'm going to switch row 1 and row 2 because I want that 1 on the top. So I get 1 and 1 on the top now. And 2, 4, 0. Three, 1, 2. Okay, and then what I can do is do some more. I can double row 1. I multiply row 1 by -2, add it to row 2. And when I do that, that 2 becomes a 0. 4 stays a 4, and the 0 becomes a -2. And then I can multiply row 1 by 3, by -3, add it to row 3. That becomes a 0. We still have a 1. And then if I take -3 plus 2, you get -1. Any questions so far? All right. Then I can switch row 2 and row 3. So I can get a 1 up there. Then I can multiply row 2 by -4 and add. And when I do that, that 4 becomes a 0. That was the whole point. And this -2 becomes a +2. All right, why am I done? Right? I mean, I'm done as soon as I look at this and say, yeah, I get it. Why can I answer the question?
0 is not equal to 2.
Right. Remember, this matrix is I did it this way because it was a little easier. I could have done the inverse matrix, except inverse doesn't work with a 3 by 2. So that wouldn't have worked with an inverse matrix. But what I can do is REF, and REF 0 is not equal to 2. So that means there's no A and B that make that equation true. So the conclusion is that that 0, 1, 2 is not a linear combination of V and W. Look at the last row of this matrix. And remember that the first 2 columns are A and B. And the third is what they're equal to. And this says 0a plus 0b equals 2. Does that make sense? So that's the 0 we're talking about. Yeah, very important that you can take a matrix and understand how it represents equations, because we use it a lot for equations. Okay, any questions on this little review of linear combinations?
So if this were to be true, we would have to have a row of zeros. At the end.
Yeah, you'd have to have in this case, you'd have to have a row of zeros.
Okay.
Right, otherwise it can't work. Because if you don't have a row of zeros, when you REF, these two here and here will be 0. So if the third's not 0, then you have 0 equals something not 0. Does that make sense?
Yeah.
Okay, so now we can get into new stuff. That was from before. Now it's time to get into now. And here comes a big major definition of the entire class, not the day, the whole course. So you got to get this down, take notes, because this is a biggie. And in fact, what I didn't do right is I didn't take this word span and I didn't put it in red and make it a lot bigger, just so I can emphasize how important this word is. Okay, so here's the definition. Let's suppose S is equal to the set V1, V2, ... Vk. So it's a set of a bunch of vectors. Then the span of S, and we denote that by span, parentheses S, is the collection of all linear combinations of vectors in S. Any questions on this definition? Any questions? Okay, it's hard to convince you immediately how important this definition is, but do you trust me? This is a really important definition. And I do have an example that will help. And that is, let's suppose we're going to look at S equals the two vectors. One, 2, 0, and 0, 3, -1. So what does it mean to be the span of S? Any questions on the question?
It should be another set of vectors that describes every combination of these two vectors, right?
Right. Now I'm, instead of using C1 and C2 or A and B, I'm going to use something different, because in the end you're going to see why, but you won't understand for a while. Okay, so what we can look at is we can look at all things of the form X times 1, 2, 0 plus Y times, actually, sorry, not X and Y. I want to go U and V is what I want. U times 1, 2, 0, and then plus V times 0, 3, -1. Any questions on that so far? Okay, now I can add those up just for fun. And we get U, comma, 2U plus 3V, comma, -V. Any questions on that basic vector arithmetic? Okay, so first thing is that this is the set of all vectors in the span. So for any real numbers U and V, any combination of U and V, they're all going to look like that. Now, looking at it like that may not ring a big bell. So instead, I'm going to think about it a little differently. And now I'm going to look at it component by component. So typically, what letter do you use for the first component of a point?
X.
X.
Oh, one. Yeah.
X. You typically use x. So I can write x, and write x of uv is equal to u. Then I could say y of uv, because these are functions of u and v, is equal to 2u plus 3v. And I could say z of u comma v is equal to negative v. Where have you seen something like this before?
Jacobians.
Maybe Jacobians, but they don't have to be that fancy. But same course.
Last. The second calculus course we took, the one where we had third, the one where we had derivatives of multiple variable functions.
Yeah, that was fourth quarter, actually.
It was fourth quarter?
Yeah.
Time moves differently during all this stuff.
That was definitely fourth quarter. So that's a fourth quarter calculus class, and Bruce did it, right? And this is these are parametric equations. And what is this? What does it look like if you had to draw this? If you had to sketch it in one word?
A surface?
Yeah, it's definitely a surface, but it's a special surface.
Is this a plane?
It's a plane. Okay, it's a plane, and I'm going to put some more words in. It's actually a plane through the origin. So it turns out, given any two vectors, then the span of those two vectors is a plane through the origin. Any questions on that? And you know it's a plane because if you take the partial derivatives, you get constants. And that's how planes work, right? Whereas if it was a u squared instead of a u, you should worry it's not going to be a plane. Does that make sense? This first guy. Okay, but since this is linear algebra, then the span of any two vectors in R3 is the plane that is determined by those two vectors. Any questions on that?
And that's always the case?
That's always the case, as long as the two vectors are not multiples of each other. Does that make sense?
Yeah.
So if they're pointing in the same direction, you're not going to get a plane. You're just going to get a line. Okay, and in fact, if it was just one vector, what do you think you get? What do you think the span of a single vector is? A non-zero vector. In one word?
Line.
A line, okay? And just to note, again, last quarter, everything was in 2 and 3 dimensions. This quarter, it's in however many dimensions you want it to be. So if this was 20 dimensions and you had to, it's kind of like it is a plane, but it's a plane in a 20-dimensional space, which good luck trying to visualize. Does that make sense? So you see how important this word span is? Because again, the span of those vectors is a plane, and planes are really important if you have two vectors. And if you have one, it's a line, and lines are really important. Okay. And as soon as you have more than two, if you have 3 vectors in 10-dimensional space, then we don't really have good language for it. So it is what it is. Any questions on this example? Okay. Let's do another example. Okay. Determine if 0, 1, 1 is in the span of 1, 1, 3, comma 2, 1, 5. So what do we have to do?
First of all, multiply them by v and u and v, and then add them.
Yeah. And I'm not going to go u and v. You could use u and v. U and v is when you want to think of it geometrically. I don't want to even think about this geometrically. I'm just going to use a and b. That's more standard. So u and v was because we were thinking of it geometrically. A and b is typically when you're not thinking geometrically, when you're doing algebraically. So we just go a times 1, 1, 3. It always makes it capital. There we go. Comma 3. And then Let me double check something. Okay. Okay, and then plus B times 215. And what's that supposed to be equal to? If it is in the span?
0, what, comma 1, comma 1.
Good, good. Okay, now I'm not going to actually continue this problem, but I want to let you know that we basically did a problem just like this already, except the language was different. So if we go back up and we look where I said, is 0, 1, 2 a linear combination of V and W? That sentence right there is exactly the same as saying, is 0, 1, 2 in the span of the set containing V and W? So I kind of did this to say, hey, it's the same thing. It's a different way of saying the same thing. Any questions on that idea?
Do you mind going back up to the definition of span real quick?
Yep. Yeah, it's a very important definition. So definitely have that down and eventually have it in your brain. So if S is V1 through VK, so it's a bunch of vectors, then the span of S, denoted by span S, is a collection of all linear combination of vectors in S.
Thank you.
Okay. And if, by the way, if S isn't just the 0 vector, then how many vectors are in the span of S?
Can you repeat the question?
So if S is not just contain the, so if S contains more than just a 0 vector, then how many vectors are in the span of S?
At least 1.
Well, that's true, but I want more specific. Yeah, infinite. Yeah, as Ralph said, there's an infinite number of vectors. Okay, there's an infinite number of vectors because you can take any constant, and there's an infinite number of constants.
Oh, yeah.
It's kind of like how many points are there in a plane? There's an infinite number of points in a plane, right? Okay, so now comes the next big definition of the quarter. I'd say the day, but it's actually the quarter. So today is a big day. Take it really seriously. If you don't have these two big definitions down, you can't pass this class because we're going to be using them pretty much every day. Okay, let's suppose again, S is a collection of vectors, V1 through VK. Then S is called linearly independent. In fact, let me make it bigger. It's that important. It's that important. I want to truly emphasize it. If C1V1 plus C2V2 plus ... CKVK equals 0 implies that CI is equal to 0 for every I. And just a note, because I'm guessing that not everyone knows that symbol. How many of you don't know that symbol?
I don't know it.
Okay, so it's an upside down A. And because we're going to be using it a lot, I want you to know the symbol. And it means for every. Okay, for all possible. So it means for I equals 1, I equals 2, I equals 3, all the way up to I equals K, this must be true. So in other words, all of the C's are 0. Does that make sense? So that's an important symbol in it, and we use it a lot in this class. Okay, if S is not linearly independent, then we say S is linearly dependent. Any questions on the definition before we do lots of examples? Okay, so notice if you look at span and linear independence, let's go back to span again. Span has to do with linear combinations. Now, linear combination means that V equals C1V1 plus C2V2 plus CKVK. Okay, so now what we're saying is that we're replacing V with 0. And I want to let you know, and this is kind of important, and it's very subtle but important. what kind of thing is this 0? Is it a number, a vector, or a matrix?
This would be a vector, right?
Yeah, it's a vector. So it's important to understand what the 0 means. I know, that seems like so easy. What is 0? Everyone knows what 0 is, except that we now have different types of 0. And this particular 0 is not the 0 number, it's the 0 vector. Okay. So clearly, by the way, hopefully it's clear to all of you, is that if you let all of the C's be 0, then you get an equation. 0 times V1 plus 0 times V2 plus ... plus 0 times Vk is 0. Do you all agree that you get 0 if you do that?
Yes.
Okay. What it means to be linearly independent means that's the only way of getting 0 with a linear combination of V1 through Vk. That there is no other way of getting the 0 vector other than the trivial solution. Any questions on this idea? Any questions? Okay, so let's do some examples. And so I'll do this one. Maybe I'll let you do the next one and give it a try. So let's suppose S is the set of vectors 1, 1, 2, 0, and negative 1, 1. We want to determine whether this is a linearly dependent or linearly independent set. Any questions on the question? All right, so how do we start? It's not tricky. In fact, let me scroll up a bit. That might help. So how do we start this guy? Yeah, we write the formal linear combination and see what happens. And you could use C1, C2, and C3, but it's the typing, especially with Microsoft Word, it's kind of messy. So I'm just going to use A, B, and C. It doesn't matter what you call them. If you have 100 of them, then you better not use A, B, and C because you'll run out of letters. Unless you're Chinese, then you can use your letters. But we're going to use A, B, and C. And we're going to say A times 1, 1 plus B times 2, 0 plus C times negative 1, 1 is equal to what?
0.
Is equal to 0. But let's write 0 now in its proper form. And that is 0, 0. Any questions on that? Okay, and that's why I wanted to emphasize that 0 is the vector, it's not the number, because we need it to be a vector. Okay, what's the next step?
Set up our matrix.
Yep, we can set up the matrix. And that'll always work, but I'm going to do the intermediate step just in case other people get lost. I can write this as A plus 2B minus C is equal to 0. And A plus C is equal to 0. Any questions on that? Just looking at the components. And now I'm going to set up the matrix, as you said. Okay. And in fact, when you really do this, you don't do any of the intermediate steps. You're going to be able to jump to the matrix, but let's see what happens. So now I'm going to write down a matrix. So let's insert. And this matrix is going to have 3 columns, 2 rows. Any questions on that? All right, and what do we get? We get 1. And I'm going to read it down. I'm going to read the columns for a reason. 1, 1, 2, 0, reading columns, and negative 1, 1. Why did I read columns? Anyone see it? Instead of read the rows. There's a reason.
Are we going to? Yeah, we're going to add the 2 rows together, and so it's better to like group them into columns. I don't know.
I mean, why didn't I say 1, 2, negative 1, 1, 0, 1 when I read this matrix? I read it as 1, 1, 2, 0, negative 1, 1. It's the same matrix, but I read it differently. I thought of it differently, even though it's the same matrix.
You
why do
thought
I want
about it as a vector.
Yeah, and it has to do with the question. Look at the question.
Oh, they're 2 by 2 vectors. So you go, okay, yeah.
You see? And notice there's nothing special about the numbers. If I made this first number a 7, then this first one would be a 7. Do you see that? So this is always going to work, is that if you ever need to decide whether a collection of vectors is linear independent or dependent, what you're going to do is you're going to write down the matrix whose columns are those vectors.
That makes so much more sense.
You see that? Now you see why I read the columns instead of read the rows? Because
it took me a second. I was like, what does it matter what difference you read it in? And then I was like, oh, okay. Yeah.
Yeah. The way of thinking about it is very important, actually. Even though, it's one of those that if I just wrote down the matrix and I just said, hey, we get this matrix, you'd have no idea whether it should be red rows or columns. But then you look at the original problem and you'll see that it needs to be read as columns because that's how we're going to be thinking about it. Okay, so now we're going to use what we did last time. Okay, now or actually not last time, a couple times ago. So this is a homogeneous system of equations. Do you see that? And when you have a homogeneous system of equations, you don't need to put the zeros. You don't need to put the column of zeros. Notice I didn't, because we had a theorem. And what that theorem say?
We can assume they're there.
Yeah, but we can assume they're there, but more importantly, if you RREF the matrix, then that'll tell you the pivots and the free variables. Do you remember that? So let's RREF this matrix, which is not a hard one. I tried to make it simple. And in fact, for this particular example, what should I do? It's very simple.
Add row 1 to row 2.
Close.
Add row 2 to row 1.
I want to add negative 1 times row 1 to row 2. I need that guy to be a 0, the second row, first column, right?
Oh, yeah.
Yeah. So I'm going to take negative 1 times row 1, turn it into row 2. Okay. And when I do that, that's a 0. Then the second guy is a negative 2. And the third is a 2. Any questions on that? All right. We don't actually need to go any further. So we actually don't need to officially REF or even RREF because we're actually done at this point. Why are we done? Why can we look at this and know the answer?
Because the last row tells us whether or not this is true.
It's different than the other example we did. Remember, this one doesn't have the equal sign. So it's not a true or not true. In fact, there's always a solution because you always have 0, 0, 0 as a solution. But what about the last column? What is the last column going to tell you? What kind of variable is it?
It's
Whether
our
or not it's equal
coefficient.
to 0, 0.
Look, it starts with an F. That's a hint.
It's our free variable.
It's a free variable because notice if the column 1 and column 2 are going to be the pivot columns. Do you see that? If you want to divide by -2, you can, but it's not necessary. And column 3 is a free variable.
And why is that again?
What?
Because it's not a pivot.
So, okay, does that mean that since column 3 is a free variable, that there can be multiple linear combinations that lead to 0, 0, and therefore it's
Exactly.
linearly independent? Okay.
Exactly. So that means we can let column 3 just say that our C equals T, right? And you can say just T is 1, for example, and then you'll get an answer. Do you see that? So C can be anything we want it to be. That's what free variable means. Do you see that? Remember the column 3 is a C variable. Column 1 is the A, column 2 is a B, column 3 is a C. And this says that the C variable can be anything, and in particular, it doesn't have to be 0. So in particular, we can let C equal 1. Anything you want. Don't want to let it be 0 because we're trying to get a non-zero one. And there's a solution. So therefore, S is, what words do we use?
Linearly independent.
One more guess?
Linearly dependent, sorry.
Yeah. Yeah. When we can get a non-zero solution, non-trivial solution, then it's linearly dependent. And that's it. We're done. Any questions on that? Any questions? All right. Why don't you try? I always like to let you give it a shot. Let's suppose S is 0, 1, 5 for the first vector and 2, 0, 0. Decide whether S is linearly independent or linearly dependent. I'm going to give you a minute or two to see if you can work this out. And the hint is very similar process. And when you've got it, type it in the chat box. And by the way, if you want to use LD or an LI, those are good abbreviations. Because linear independent is a lot of letters, and linearly dependent is also a lot of letters. So LD and LI will work in this class, and everyone will know what it means. And I'm waiting until a couple of you get it, and then I'll work it out. All right, let's work this out and see. Okay, so the first thing, I'm going to kind of follow the same method. I'm not going to show all the intermediate steps because I can jump right to it, and I can write down the matrix. And that's what I'm going to do. Hopefully, you'll be okay with what I do. But it saves a lot of time if you just write down the matrix. So let's make a matrix. Notice that the vectors in S are the columns, not the rows. So you get 0, 1, and 5. We get 2, 0, 0. Any questions on setting up the matrix to help us determine if these are linear dependent or independent? Okay, then we're going to REF. So I'm going to switch row 1 and row 2. Any questions on that? Okay, then I'm going to multiply row 1 by 5, by -5, and add to row 3. And when I do that, row 3 becomes a row of zeros. Okay, now take a look at what we get. Notice that for the first and second columns are both pivots. How many free variables do we have?
We don't have any.
We don't have any. There
So that
are
means
no
it's
free
independent,
variables.
not dependent.
So the system has only the trivial solution. And when you only have the trivial solution, that's the definition of linearly independent. So S is Li, linear independent. So I want to make sure you understand, because based on the chat box, that's not what you guys got. And it wasn't a trick question or anything. You just RREF the matrix of column vectors, and then see if you have any free variables. And here everything's a pivot, so there's no free variables. Any questions on that? Does that make sense, or is it confusing?
No, it makes sense. I was just kind of confused about doing RREF since, like, we've been doing it with square matrices, and so when I saw one where the rows didn't equal the columns, I got all confused. It was totally on my end.
Yeah, but remember, I know in this week we've been doing square matrices, as in Monday and Wednesday. Before that we didn't, though. So now we're back, sometimes square, sometimes not square. Okay, here's another question. This one's a little weirder. Let me make it its own page. Okay, let's suppose S is now the set UVW. And let's suppose that S is a linearly independent set of vectors. Then I'm going to make a new set of vectors, T, where the first vector of T is 2U minus W. The second vector of T is 3V. And the third vector of T is V plus W. Okay, the question is T linearly independent or dependent? Any questions on the question? Okay, how do we do this?
Set up two matrices.
Yeah, but we're not quite ready for the matrices yet. There's going to be, actually, we're not going to have two. We're going to have one matrix, but we're not ready yet. This one, you got to go with the definition. And what does the definition tell us we need to do?
Linear combination.
Yeah, we're going to write a linear combination, and I'm just going to use ABC. So we're going to have A times 2U minus W plus B times 3V plus C times V plus W. And I set that equal to what?
T, right?
Not T.
No, 0, right?
Zero, the zero vector. Because that's what the definition of linear independent means. Any questions on that? All right, and notice that A, B, and C are scalars, and U, V, and W are vectors. So it's important to notice that. Okay, now what can we do? Any ideas?
Why don't we need to know the dimensions of U, V, and W?
Makes no difference. Make it 300 dimensional. I'm good with that. Sound good? You could do it 10,000 dimensional. It makes no difference at all. So the answer is it doesn't matter. So I'm just saying some dimension, n dimensional. That way it is. Okay. And by the way, if I ever write something like U, V, and W, that means they're the same dimensions. So you can't, it doesn't make any sense for U to be a 5-dimensional and W to be 2-dimensional because you can't add them. So just, they have to be the same dimensions. But any dimensions, doesn't matter. So any idea what I can do? The hint is it's easy. Huh?
Multiply with
Yeah, multiply. And I'm going to do 2 steps at once because you guys are linear algebra students, which means that you should know algebra really well. I'm going to combine like terms. Sound good? And I'm going to look at the U term. And I'm going to say that's 2A. 2A times U. And then I'm going to look at the V term. And the V term is going to be 3B plus C times V. And then I'm going to look at the W term, and that's going to be negative A plus C times W, and that's equal to 0. Everyone good with that?
Yep.
All right, we're pretty close now. All right, we know that UVW, that set is linearly independent. So the reason I rewrote it is now I can use the fact that U, V, and W are linear independent. So since they're linear independent, what do you know reading this second equation? Because U, V, and W are independent, and I have a constant times U plus a constant times V plus a constant times W equals 0, what do I know?
That U, V, and W are trivial solutions.
Not that U, V, and W are solutions. U, V, and W are just the vectors given. But something about trivial.
A, B, and C must be 0.
Not quite. Not quite A, B, and C. Any ideas? So what it means is that the coefficients in front of U, V, and W are all 0. So the coefficient in front of U is 2A. The coefficient in front of V is 3B plus C. And the coefficient in front of W is negative A plus C. So what I can say now is that 2A is equal to 0. 3B plus C is 0. And negative A plus C is equal to 0. Anyone lost on how I came up with that? Based on the fact that S is linearly independent. All right, now what can I do, given the fact we've been spending the last 3 weeks doing it?
Set up our matrix.
Yeah, now we can set up the matrix. So now I set up the matrix. There's always going to be matrix, you notice that? But usually it takes a while to get to it. So I'm going to set up a matrix. And this is going to be 3 rows, 3 columns. So it's a 3 by 3. And the first row will be 2, 0, 0. The second row will be 0, 3, 1. And the third row will be negative 1, 0, 1. Any questions on that?
So how do you determine whether or not you want to look at the matrix as a set of numbers or vectors?
You mean think about as a set of numbers or vectors?
Yeah.
Well, like on this one, we don't have a set of vectors from this example, like that we could put in with numbers. Do you see what I mean?
Yeah.
You couldn't even do it. Does that make sense? Whereas the other one, we're given S as a set of vectors. So if you just want to find out if these vectors are linear dependent, just write them as a set of column vectors. But for this example, it doesn't even make sense to say, I'm going to write these as a set of column vectors, because what would the first column be? Do you see? And yes, it's 2, 0, negative 1, but you got to get to it first. It is because they're the coefficients, but you got to see it. Does that make sense?
Yeah.
Now, this one's not as obvious. But what should be as obvious is how to RREF. So I can divide the first row by 2. You good with that? Just wants to be. Then I can add the first row to the third row. Any questions on kind of the steps of RREFing? Now I could switch. Oh, sorry, I can, at this point, I'm done, actually. I don't even need to do any more. Why am I done?
Each column has a pivot.
Yep, each column has a pivot. This is a 3 by 3 matrix, right? So it's a 3 by 3 matrix. This only has a trivial solution. So now we know that A and B and C are 0. So only the trivial solution exists. So T is linearly independent. Any questions on this example?
Yeah, why doesn't the second row contain a free variable?
It's a pivot.
Yeah, but there's a 1 too.
I can get rid of the 1 if I want.
Okay.
RREFing, right? But as soon as I have a triangular matrix, triangular matrix where I don't have any zeros, then I'm good. Do you see?
Okay. Yeah, that makes sense, because you can eliminate the things that aren't 0. Okay.
Yeah, I could even use some theorems and say, hey, what's the determinant of this matrix?
3.
3, not the original matrix, but the point is 3 is not 0. So the determinant is not 0. So by TFAE, A is invertible. And if A is invertible, right, because we got a square matrix here. So A is invertible, the capital A is invertible. That means that only the trivial solution exists, because we can say that ABC equals A inverse times 0, 0, 0. So A and B and C are all 0. Does that make sense?
Yeah.
Yeah, so you could also do it with determinants, but instead I just did it with pivots. There's lots of ways of thinking about these things. Okay, any questions on this example? All right, this is a theorem, and I want to tell you to be careful. So let S equal the set of vectors v1 through vk. Then the following are equivalent. And I want to note something. I did not capitalize the following are equivalent. I did not write TFAE because this is a different following are equivalent. Okay, but hopefully you know what following are equivalent means, but it's not the standard. It's not our big following are equivalent. It's just a new following are equivalent. Got it? Number one is S is linearly independent. Number two is no vector V in S is in the span of the set of vectors in S after V is removed. Okay, so if I take out, say, V2, then V2 will not be in the span of V1, V3 through VK. Okay, and you can and no vector will work that way. And number three is that if A is the column vector matrix, then AX equals 0 has only the trivial solution. Okay, so this is a big theorem. It's a very useful theorem. It's not the big theorem, though, just let you know that. We've kind of seen 1 and 3 together. Do you agree? That's kind of how we did the first couple examples. Isn't that what we did? Is we wrote the matrix with column vectors V1 through VK, and then RREF'd it, and then saw if AX equals 0 had the trivial solution only. Isn't that what we did? Do you all follow that? So I thought I'd prove 1 and 2. Okay, and that means that if S is linear independent, so let me give you a proof of part of it at least. If S is linearly independent, okay, then we know what that means at least. So I guess I shouldn't say S, let S be, even better. So let S be linearly independent. And what we want to do is we want to show that no vector V in S is in the span of the rest of them. Then one big method of proof, and I'm not sure if you've seen this before. You should have seen it in high school geometry, but high school's kind of watered down the geometry, so you might not have. But this is what I'm going to do, and that is one way of proving something is true is to suppose that it's not true, and then show that you end up with something that can't be true, can't be right. And that's called proof by contradiction. Have you heard that before?
Yeah.
Okay, so I'm going to prove this by contradiction. Then I'm going to say, then suppose that, let's say VI, that V1, I need to make an equation so I can get subscripts. Okay, is in the span of T, which is equal to going to let me. Well, we'll do that. Ooh. V sub 2 through VK. And I'm going to write down something that you may not have seen before. Have you seen those initials, WLOG? You haven't seen those?
No, I haven't.
Okay, so it stands for without loss of generality. So again, there's a lot of initials and symbols in proofs, and these are big ones. So they'll call this a W log proof. So it's without loss of generality. So the idea is what I said, well, I'm just going to pick on V1. And the idea is, let's, if it was say V7 instead of V1, just reorder. The order doesn't matter that you write these vectors. Do you agree? Being linearly independent has nothing to do with what order you write them in. Do y'all agree? So I'm just going to say, let it be V1 just because it's easier to type. So let's suppose that V1 is in the span of this T. So if it's in the span of that T, I need to make a new page out of it. So if it's in the span of that T, what does it mean to be in the span? Any idea? I know the first day we've ever heard that word, but that's how we started.
The collection of all linear combinations.
Yeah, so exactly. So that means that there's going to be constants, and I'm going to label it. Usually you start with a C1, but since it's a V2, I'm going to call it C2 V2. Doesn't matter what you label the constants. So let's do that. Then C2 V2 plus ... plus CK VK is going to be equal to V1. For some constants, C2 through CK. Isn't that what the span means? Are y'all good with that?
Yeah.
All right, what can I do now? And the key is you got to know what your goal is. And our goal is we said let S be linear independent. And now we're going to try and show that we have a contradiction if we have this in the span. So a contradiction means that we're going to try and show it's not linear independent. Does that make sense? So what can we do?
We could look at 2. It says no vector V and S is in the span of the rest of vectors in S.
Right. But we're saying suppose there is one in the span, and I'm going to try and find a contradiction. So I'm already looking at number 2. So we started with the opposite of number 2, and we're going to show that we have a contradiction. So we already did that. So we want to show they're linearly dependent. The hint is it's a very easy step, but it's only easy if you think about what to do. Any idea? Then here's what I can do. I can take that V1, I can subtract V1 on both sides. Very basic algebra, do you agree? Are y'all good with that? But why does that show that S must be linearly dependent? Why can I say that?
Because we have a free variable in C?
No, there's no matrix here. No, it's a very simple explanation, but you have to know what you're looking for.
We remove B1.
Not quite. It's very simple.
There's no C1.
There is a C1, and that's the whole point. What is C1?
0.
2. It's one more time.
-1.
It's -1.
At the end. And sometimes
Oh, since C1 is just one thing, it's -1.
It's -1. And what is -1 not?
It's
Zero.
not 0.
Not equal to 0. And that's what it means to be linearly dependent. It means that if we write down this equation, you can find a list of constants that they're not all 0, and it's still true. And guess what? They're not all 0 because the first one's a 1. Do you see that? So this is proof. So therefore, 1 implies 2. It's called proof by contradiction. Is that if you show 2 is false, implies that 1 must have been false. That means if 1 is true, then 2 must be true. Any questions on that logic? Make sense? Okay. So that's one direction. I'm not sure if I have time to do every direction, but that's one of the directions. If I want to go from 2 to 1, what would I have to do? Because I have to do all these, for a TFE, I have to do every direction, right? So suppose if you want to go from 2 to 1,
you would have to remove V and then show that it's not true, because it says V, no vector V in S is in S after it's removed.
right?
So, no, I don't know actually. No.
All right. So the idea is you do it in the same way. You do proof by contradiction. So you say, suppose S is dependent, and then you're going to say, if S is dependent, then there must have been a vector. Do you see that? So we show if 1, so 2, you want to show 2 implies 1. That means if 1 is false, then 2 must have been false. Do you see that? So if S is linearly dependent, then, well, what we do is we write down the linear dependence relationship. Then C1 V1 plus C2 V2 plus dot 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 CK VK is not 0. And one of the C's is not 0. And I'm going to do W LOG. C1 is not equal to 0. Any questions on that so far? But if that's true, then what I can do is I can solve for V1. And I can say that V1 is equal to, it'll be negative C2 over C1. And notice I'm allowed to do that because C1 is not 0, so I can divide by C1. Plus dot 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 plus CK over C1. I made that. There we go. And it's actually minus, oops. Is it minus? Yeah, it's minus because we brought it over. There we go. And that's all I needed because guess what? I've just written V as a linear combination of V2 through VK. So therefore, V1 is in the span of the rest. So 2 is false. So that's a proof by contradiction. Therefore, 2 implies 1. Anyone lost on what just happened?
A little bit. So why can we say that V1 is in the span of the rest? Is because we're left with constants?
Okay, what does it mean to be in the span? It means you can write it as a linear combination of the rest, right?
Yes.
Well, I just did.
Ah, okay.
Constant times V2, and then plus constant times V3, plus dot, 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 plus a constant times VK,
Okay.
right? And what allows me to do this is that C1 is not 0. Okay, because if C1 is 0, I can't do that because I just divided by 0. Do you see that? So I
Yeah.
needed that. I needed the C1 to not be 0. I needed linear dependence, which means something has to be non-zero. And I'm going to say, let's just call that the first one without loss of generality. And that's a proof of this theorem. Any questions on this? Was I right that today's a pretty theoretical day? Or very theoretical? So we'll have some that are and some that aren't. Okay, here comes the next theorem. And this theorem, again, I call it the too many vectors theorem. You can call it what you want. The book doesn't have a name for it, but it helps you remember. And let's suppose that S is equal to V1 through Vk is a set of vectors in Rn. So now I'm actually specifying Rn. Then if K is bigger than N, S is linearly dependent. Okay, so for example, if we had R3 and we had 4 vectors in R3, then those 4 vectors in R3 as a set is a linearly dependent set. Any questions on the theorem? Any questions on what this says? So if you have too many vectors, you can't be linearly independent. Okay. It's a very simple proof. How do you prove it? Any thoughts? Okay, if you don't know, let me show you. What we do is we consider.
I have an idea.
Uh-huh.
So if you wanted to set up a matrix to test whether or not it was linearly dependent or independent, you're going to
Good.
end up
That's
with
what I'm
free
going to do.
variable because it's not square.
Yeah, so we're going to write down V1. It's even worse than not square. Not square is not enough, actually. You
There's,
need to actually have the inequality correct. You need K to be bigger than N. If N is bigger than K, then it can be linearly independent.
there's more rows than columns.
Yeah, that's what you need. So we have V1, more columns than rows, you mean? So there's more columns than rows.
Yeah.
V1, and then V2. And then VK. And let's call that A, the matrix. Okay, so A has more columns than rows. So now our REF of A, or REF, but we're doing in theory, so it doesn't matter how many R's. Our REF of A, well, what you know? What you know is that cannot have pivots in every column. Do you agree? Any questions on that?
No, that makes sense.
Yeah, you can't have pivots in every column because because you get one pivot per row at most. And there aren't enough rows because that's why K is bigger than N. Okay, so our REF of A cannot have pivots in every column. Therefore, there are free variables. It could only be one, but that's okay. You get at least one. So the linear independent equation has a non-trivial solution. Right? As we saw in our examples, if you have a free variable, then that tells you you have a non-trivial solution because let that variable be 1.
What if K is less than N?
So if K is less than 1, then this is not a theorem. This doesn't work. So if K is less than N, you could have linear independent, you could have linear dependent, either could happen. So we could even, since we have some examples, let's scroll. Let's do an example. So do I have a K is less than N? That one. Okay, so here's an example. Here's an example where we found they were linearly independent, right? Do you agree?
Yes.
Okay, but no, I'll put it here. That if, well, I'll call it T now, since we already used S. If T is a set, I'm going to make it really easy. 1, 1, 1, comma 1, 1, 1. Pretty boring set. Is linearly dependent. Do you agree those are dependent?
Yeah.
Yeah. You just say 1 times the first plus -1 times the second is definitely the 0 vector. That's an example. Okay, so that makes it linearly dependent. But here, K is less than N, right? We have 2 vectors in R3. So either could happen. So, which is why there's no theorem.
Got it.
Right? You never write down a theorem saying, given a bunch of stuff, we know nothing. And that's what that theorem would be, which isn't very interesting. Okay, so let's move back. That was the too many vector theorem. Okay, we don't have too much time and I need to get to these guys. All right, but this example, prove that S equals 214, 326, -508, 111 is linearly dependent. How do we do that in 10 seconds?
K is greater than N.
Exactly, but let's state them. What's K?
So by the too many vectors theorem.
What's K? What's K?
The columns.
No, I'm not looking for a number.
4.
What's 4? 4 is greater than
3.
3. So by the too many vector theorems. S is linearly dependent. And that's it. Was that an easy proof? Isn't that wonderful? So this is one of the easiest proofs, easiest theorems to use, because I just count. Okay, the next theorem is if S is equal to V1 through Vk, and let that be a linearly independent set of vectors, then any vector in the span of S can be uniquely written as a linear combination of vectors in S. Okay, why must that be true? Very simple proof. And I'm going up here just so I can copy and paste, so I don't have to keep typing. There we go. That one. So let's suppose that we have C1, V1, dot, 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 CK, VK, add them up, is equal to, in this class, I can use D without a problem. D1, V1 plus D2, V2 plus DK, VK. And we want to show that the C's and the D's are all the same. So C1 equals D1, C2 equals D2, etc. I got to make that a 1. Oops. So I could do something very simple. What is that? The hint is I want to use linear independence. What do I want on the right-hand side if I want them to be linearly independent?
0.
I want a 0. So I just subtract. Then C1 minus D1 V1 plus C2 minus D2 V2 plus dot, 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 plus CK minus DK VK equals 0. Now they're linearly independent. So what can I say about these coefficients?
The coefficients in front of B1, B2 must be 0.
Yeah.
Okay.
So by linear independence, the CI minus DIs are all 0. And that's what we want. Therefore, we get uniqueness. So uniqueness means that you have the same way of writing it. You can't have 2 different ways of writing. And that's the proof. Okay, so a big corollary is that if we have if S is linearly independent, then T equals V1, V2 through VK, comma VK plus 1 is linearly dependent if and only if VK plus 1 is a span of S. And that comes right from the theorem. Any questions on that? Any questions? All right, since we're running out of time, I want to jump to the big theorem. And that is TFAE, growing. So let me review all the ones we've already had. A is invertible. RREF of A is 1. Determinant of A is non-zero. Now we have 4 new ones. The columns of A are linearly independent. The rows of A are linearly independent. Okay, the columns of A span Rn, and the rows of A span Rn. Okay, notice 4 and 5. How can I immediately show 4 and 5 will work? The idea is, how do you switch the word row to column? Transpose. And if we had a theorem earlier that if A is invertible, A transpose is invertible. In fact, I could even, if I felt like it, I could add that to TFAE. A transpose is invertible. So the row to column, that's immediate. But we've also talked about looking at whether we have linear independence by taking the matrix and then counting the pivots. And the idea is that if we have a square matrix when we do it, then that means that we have the right number of pivots. Do you see that? And that's all we need. Okay, so that means that we have n pivots. If you have n pivots, they're linear independent and it's invertible. Any questions on that? When you RREF it. Okay, what about the span? The column span Rn. Okay, so if the columns don't span Rn, that means we can add another vector in there. and get linear independence. Is that clear? That was the last theorem. You know, the corollary is you can just add another one. Okay. Well, that's going to be a problem because if we had an invertible matrix and you add another one, it can't be invertible if it's not square. So all kinds of things happen there. Again, we're running out of time, so I can't do the full proof of this, but it is in the book too. And similarly, rows and columns, you can switch those and it doesn't matter because that's transpose. But I am out of time. I'm a couple minutes extra. It's really hard to get exactly 2:45 with this online stuff. So I'm going to stop the share and stop the recording.